7 terrifying discoveries in space. The sky looks calm tonight. No cracks, no distortions, no warning lights in the dark. And that's the problem, because for most of human history, we looked up and assumed order. Predictable stars, clean orbits, a universe that followed its own rules quietly. Then the measurements started coming back wrong. Not wrong like error. Wrong like something is out there that we haven't named yet. A radio signal 72 seconds long that appeared once from across the galaxy and never repeated. Flashes of energy that outshine entire galaxies in milliseconds. A star dimming by 20% with no planet large enough to explain it. Matter holding galaxies together that no instrument has ever directly detected. Black holes, hundreds of millions of them drifting through the Milky Way in silence. A universe accelerating apart when gravity should be pulling it back together. And an equation suggesting that reality itself may not be in its final state. These are not science fiction scenarios. When the universe reveals a gap in our understanding, history has shown the answer is often bigger than we expected. Tonight, we step into those gaps. August 15th, 1977, Ohio, United States. A radio telescope was scanning the sky, not searching for anything unusual, just listening. Routine survey, background noise, the steady, quiet hiss of deep space. Then something cut through the static. For 72 seconds, a narrowband signal surged to nearly 30 times the background level. Clean, sharp, precisely concentrated at 1420 megahertz. That frequency is not chosen at random. 1420 megahertz is the broadcast frequency of hydrogen, the most abundant element in the universe. For decades, scientists had reasoned that if any civilization wanted to announce itself across the cosmos, this is the frequency they would choose. A cosmic landmark, a universal constant, a signal fire built from physics itself. When astronomer Jerry Eman reviewed the printed readout, he circled the data sequence, then wrote a single word in the margin. Wow. The signal appeared to originate from the direction of Sagittarius, near the dense star fields toward the center of the Milky Way. Then it stopped. It never repeated. That's the detail that still unsettles researchers today. Not its existence, its silence afterward. Terrestrial interference satellites, aircraft, ground transmitters was ruled out. The signal was too narrow, too precise, too clean. And it did not drift in frequency the way human-made signals do. Follow-up observations scanned the same region. Nothing. For years, then decades. Comets were proposed. Unknown astrophysical processes were debated. No explanation has fully accounted for the signal's strength, duration, and frequency profile. It remains officially unexplained. Scientists do not claim the WOW signal was artificial. They claim something simpler and more unsettling. We do not know what produced it. The Milky Way contains hundreds of billions of stars. It has existed for over 13 billion years. A single unexplained signal in that scale is not trivial. For just over a minute, something pierced the cosmic silence. Then the silence returned. It has remained unbroken ever since. In 2007. Astronomers reviewing archival data from the Parkes Observatory in Australia noticed something strange. A radio pulse, not lasting 72 seconds, not even 1 second, a few milliseconds. And yet, in that fraction of time, it released as much energy as the sun produces in days. Many scientists suspected equipment interference at first. Even microwave ovens had fooled radio observatories before. But then it happened again and again. Different telescopes, different continents, different years. Short, violent bursts of radio energy appearing randomly across the sky. They were named fast radio bursts, FRBS. Each one lasts only milliseconds, but in that blink, some emit as much energy as entire galaxies radiate in radio wavelengths. The dispersion of the signals, the way different frequencies arrive at slightly different times, revealed something critical. These bursts were not local. They were extragalactic, billions of light years away. In 2020, astronomers traced a fast radio burst to a magnetar inside our own galaxy, a neutron star with a magnetic field a quadrillion times stronger than Earth's. This was a breakthrough. It confirmed that at least some FRBs can be produced by extreme stellar remnants, but not all of them fit neatly into that explanation. Some FRBs repeat, others never do. Some show complex structures, multiple peaks, drifting frequencies, strange polarization patterns. One repeating source exhibits a 16-day activity cycle. Another is embedded in a magnetic environment unlike anything previously cataloged. Estimates suggest thousands of fast radio bursts occur across the observable universe every single day. We just don't detect most of them. The universe was flashing signals at us constantly, and we lacked the instruments to notice. That realization is quietly profound. If phenomena this powerful went unnoticed until 2007, what else is happening beyond our current detection limits? The universe is not silent. It is erupting in millisecond flashes powerful enough to cross billions of light years, and we are only just beginning to decode them. Stars are supposed to be predictable. A planet passes in front, brightness dips slightly, it returns to normal. Repeatable, clean, periodic. That's what NASA's Kepler Space Telescope had been watching 150,000 stars, searching for exactly that pattern. Then one star broke the pattern entirely. KIC 8462852, known now as Tabby's star. Instead of regular dips, this star dimmed irregularly, not by 1%, not by 2%, sometimes by more than 20%. That is enormous. To block that much light, an object would need to be massive, far larger than any planet. And yet the dips were not periodic. They didn't repeat on a clean orbital schedule. They appeared chaotic. Sharp drops over days, slow fades over months. No pattern, no explanation. Astronomers searched for ordinary causes first. Dust clouds, comet fragments, instrument error. The data held up. Spectroscopic analysis showed that when the star dimmed, certain wavelengths were absorbed more than others, consistent with fine dust particles, not solid objects. That ruled out megastructures, but it raised a different question. Where was the dust coming from? Why was the dimming so irregular? And why had the star also appeared to fade gradually across a century of historical photographic plates? Tabby's star is not supernatural. It is not evidence of alien engineering. But it is a reminder that even in our own galaxy, stars can behave in ways we don't immediately understand. Look at a spiral galaxy. Hundreds of billions of stars orbiting a bright center. Arms stretching across tens of thousands of light years. One of the most beautiful structures in the universe. Now, measure how fast those stars are moving. According to Newton's laws and Einstein's refinements, stars farther from the center should orbit more slowly, just like the outer planets of our solar system. The farther out you go, the weaker gravity becomes. That is what the equations predict. But when astronomers measured galactic rotation speeds in the 1970s, something didn't match. Stars at the edges of galaxies were moving far too fast, fast enough that they should be flung into intergalactic space. But they weren't. Every galaxy measured showed the same result: flat rotation curves. Outer stars orbiting just as quickly as inner ones. The visible matter, stars, gas, dust, wasn't providing enough gravity. Something else was there, something invisible. It neither emits nor absorbs light. It does not reflect radiation. It interacts gravitationally and almost nothing else. We call it dark matter. Based on cosmological measurements, dark matter makes up about 27% of the universe. Ordinary matter, everything we can see, touch, and measure directly, accounts for less than 5%. Most of the universe is composed of something we have never directly detected in a laboratory. Its existence is inferred. Its nature is unknown. Underground detectors, shielded from cosmic rays, were built to catch rare interactions. So far, nothing conclusive. Particle accelerators have searched for candidates. No confirmed detection. And here is what makes this quietly unsettling. Galaxies, including our own Milky Way, are embedded inside massive halos of this invisible material. It surrounds us, passes through us, anchors the cosmic web. Without it, galaxies would not form as they do. The universe, as we observe it, depends on something we cannot see. We are living inside a gravitational architecture built from an unknown substance. Most of the cosmos is invisible, and we are still trying to understand what it is made of. Black holes are often imagined as monsters at the centers of galaxies, and that part is true. At the heart of the Milky Way sits a supermassive black hole, 4 million times the mass of the Sun. But not all black holes stay anchored. Some wander. When a massive star dies, it collapses under its own gravity. If the core is heavy enough, nothing can stop it. Not radiation pressure, not nuclear fusion. Gravity wins. A stellar mass black hole is born. But supernova explosions are not always symmetrical. If the blast kicks unevenly, the newly formed black hole can be launched through space. Silent, dark, moving. In 2022, researchers reported the first confirmed evidence of an isolated black hole drifting through the Milky Way, detected not by light, but by gravitational microlensing. The object emitted no radiation, no X-rays, no visible glow, nothing. Its presence was inferred because it bent the light of a distant background star as it passed in front of it. A brief distortion, a subtle brightening, gravity revealing something otherwise invisible. Estimates suggest our galaxy may contain hundreds of millions of stellar mass black holes. Most are quiet, unaccreting, dark, drifting, and we cannot map them all. If one passed through the outer solar system, we might not detect it until its gravitational effects became measurable. It wouldn't swallow Earth. Black holes are not cosmic vacuum cleaners, but its gravity could disturb our comet clouds, alter long-period orbits, send icy bodies inward toward the inner planets. The probability of a close encounter is extremely low. For most of the 20th century, astronomers assumed something simple. The universe began expanding with the Big Bang. Gravity would slowly pull everything back together. Expansion should be slowing down. That was what the equations said. Then in 1998, two independent research teams studying supernovae across billions of light years made a discovery that shocked cosmology. The universe wasn't slowing down. It was speeding up. Distant supernovae appeared dimmer than predicted, meaning they were farther away than expected. Expansion wasn't decelerating, it was accelerating. Something was pushing space itself apart. That something was named dark energy, not because we understand it, but because we needed a name for the thing we couldn't explain. Current measurements suggest roughly 68% of the universe is dark energy. Nearly 3/4 of everything that exists is driving this acceleration, and we do not know what it is. Dark energy determines the ultimate fate of the universe, and that fate depends on a force we cannot directly detect. If dark energy remains constant, galaxies will drift farther and farther apart. Stars will exhaust themselves. The cosmos will grow colder and darker. If it strengthens over time, expansion could eventually tear apart galaxies, then stars, then atoms themselves. If it weakens, expansion might stabilize. We do not yet know which path is correct. For the first time in human history, we can measure the large-scale fate of reality, and that fate depends on a force we have never been able to touch. This one comes from the equations themselves, not from space, not from distant galaxies, from the mathematics of quantum field theory. The vacuum of space is not truly empty. It has energy, structure, a baseline state. Physicists call this a vacuum configuration. And here is the disturbing part. That configuration might not be the lowest possible energy state. It may be what's called a false vacuum, stable for now, but not the absolute minimum. Imagine a ball resting in a shallow valley on a hillside. It looks stable, but somewhere deeper down the slope is a lower valley. If the ball were ever nudged hard enough, it would roll to the true minimum, releasing energy in the process. Now replace the ball with the entire universe. Calculations using the measured mass of the Higgs boson discovered in 2012 at CERN suggest our universe may sit close to the boundary between stability and metastability. The numbers are tight, within experimental uncertainty. If the Higgs field transitioned to a lower energy state, it would not explode outward like a bomb. It would form a bubble, a region of space where the laws of physics are different. That bubble would expand at the speed of light. Atoms would no longer hold together. Forces would rebalance. Chemistry would fail. There would be no warning. Because the bubble would travel at light speed, we would not see it coming. The first sign would be the last. This is not a prediction. It is not expected to happen anytime soon. Current models suggest that if the vacuum is metastable, its lifetime would vastly exceed the age of the universe by unimaginable margins. But vastly longer is not the same as infinite. High-energy cosmic events have bombarded the universe for 13.8 billion years without triggering a transition. Particle collisions far more powerful than anything in our accelerators occur naturally in space, constantly. The universe remains intact. But the possibility remains embedded in the equations. Vacuum decay would not come from outside. It would come from the fundamental structure of reality itself. It's a reminder that even the constants we rely on, mass, charge, the strength of forces, may not be guaranteed forever.